Okay, morning class. So hope everybody get a good sense about this question from the last lecture. It's all about structure factor, okay? So before I want to start today's lecture, I want to address some of the questions we got from the last one. Especially the first one. I think that's some of you didn't get this one fully correct. So let me try to spend 10 minutes or so to explain how do we get this particular question, because it's more relevant to how you measure a sample and down the road how you prepare a good test. Okay? So how do we measure a scattering vector Q and the intensity? Because all our discussion is based on we can get a plot of I and Q for our data. So whatever sample you put in, if we can get I and Q plot, we can do analysis to it. But first step is we need to get this particular plot. So it's not that hard, but do have a little bit interesting factor I want to talk about. So first is how do we get the scattering intensity? We got a couple slides. I want to go back to here. And I stolen some of the slides from Luke, made for a couple months back for our X-ray school. So X-ray is all detected by X-ray detector. So how do we measure intensity and Q? All comes from this X-ray detector. So in the early days, X-ray detector is as simple as just a film, a photography film. Actually, people use to measure the X-ray. Think about how Ron Jim first discovered X-ray. There's no any electronic devices to measure it, so it's just a very simple chemistry. When you're exposed to X-ray, you have chemicals that are sensitive to it, can be developed very much like a film people used in old school film camera. But with the technology development, we have now CCD technology or CMOS technology. Two of the predominant technology used in your cell phone or photography camera. Same here, but the difference is we are more geared towards detection of high energy X-ray. So the platters is most dominant technology used for several advantages. So it's much better in terms of readout time. That means how much time for you to read the data stored in each pixel. So in this white screen below it, it's basically the CMOS. If you ever own the camera or single, you open it up, you can see the lens there is basically detector, photolithography technique made, very nice detector. So it's inside this. So this is a protective film on the top. And how it works is basically by generating a photodiode. When you X-ray hit the material, you can generate photons and use the photons to generate exciton, and you can split charges, very much like a solar cell devices. Okay, those are more technical detail, but in a short sense, we now develop the electronics can measure every single photons to your detector. It's that accurate. One photon hit it, we can amplify it and measure how much intensity out of there. Okay, so we can get very good results in terms of intensity. So you can imagine a camera is also defined how many pixels in it. When I was at my high school college, we are talking about Kodak, who is a company made the CCD, and they make 1 million pixel cameras, point and shoot. Very, very, very low pixel densities. Nowadays, you're talking about cell phones can take 20 megapixel images, right? So same here, the resolution of the detector is defined by two things, is how each pixel size is. In here, we typically arranged by about 1,000 pixel by 1,000 pixel. And each has a certain pixel size, okay? So these pixels are basically individual detector, can detect any photons hitting there. So this is a typical image many of you might be familiar with. So this is already from, we convert from pixels to qx, qy, is scattering vector. But when we collect the raw data, it's actually pixel. And why we see this kind of ring here is just because the pixel at these ranges detect a higher X-ray photon, okay? So the detector basically records pixel 1, 1, pixel 1, 2, basically each of them, all the way to pixel row 1, pixel 1000, reports how much pixel I detect from my individual pixel. Then you can plot them as an image, very much like that. So from this image, we record two things. Very importantly, intensity and where the most intense scattering happens at which pixel, right? So intensity is easy, right? Now how about the scattering vector Q? How do we detect the scattering vector Q in the last quiz? Some of you got there, right? But still, there are some questions, and I'll explain a little bit more detail. Let me come here. Use this. Let me just go to an open slide and explain. Let's create a new slide. Insert, new slides. Hold on. That's a little bit difficult. Copy, paste. Delete. Okay, now we have empty slides. Perfect. So go back to the image. We have a detector on the right? We have X-ray beam coming in. You have a sample here. Some of the beam will pass, and some of them will scatter. And you are able to record the pixel in the detector. So you need to answer what the theta angle is. Because we talk about Q is equals to 4 pi sine theta divided by lambda. In this particular case, we need to answer what this theta angle is. It requires 2 parameters to get this theta angle. Okay, exactly 2 parameters. You need to know this length and this length. So you can calculate out. Sorry about that. So we can call it distance d in here. We can call it this L. So you can know tan theta is equals to d divided by L. And in a typical X-ray setup, the L is defined. Where you set the detector, what's the distance from center, is defined by your sample geometry. And we will talk about, we have ways to measure it. So this is known, right? What L value is. We can measure it pretty easily. If you know where the sample is, where the detector is, this is defined. So now how about D? D is not hard as well. D is given by counting basically the distance from the beam center, where the beam is hitting the detector, to where your diffraction signal is. Okay. So D basically, in an X-ray detector, we count how many pixels from the center, multiplied by pixel width. Okay, so this is how we count the D. And we have specialized software basically convert these pixels to Q. That's why if we go back, right here, you know where the center is? and you know where your scatter bin is, the software will be able to read how much pixel from here to here, convert into a real space. And as long as you know STD, sample to detector distance, what we short for STD, you can calculate this scattering angle. And it's usually done automatically by software, and we will cover that part in a later, how we can correct this value.
I was going to ask more about that, because if you have a beam stop, how do you gather true max intensity?
Good question. How do we know where the beam center is? Anyone want to guess? Look, how do we get the beam center?
We can use, well, we can do two things. One is, the easiest is using a standard silver bahana that gives a very strong and predicted scattering pattern, and then we then fit that pattern to get the beam center. Or if you wanted to do it very manually and not in a good way, you could actually move the beam stop and get the center from that.
Yeah, so very good answer. So 2 ways. Our detector is a special one, and our beam source is very weak. So this, let me emphasize, only applies to lab source instrument. You can move it away the beam stop, which is basically block the direct beam, so you don't see it here. You remove it, you can basically measure where the direct beam is. That's one way, but nowadays nobody almost use that way, because if we saw this ring, if we know the ring pattern, their software actually can compute where the center of this ring is. That's where basically your scattering direct beam is. So that's how almost every single technique does at the synchrotron, because if you move the detector, you shoot a synchrotron we're talking about, that is millions times more intense. You're going to destroy that particular pixel because you overloaded it so much with, okay? So don't move the detector beam stop away. Just to put a standard sample, then usually we put in very strongly scattered sample. So particular this case, where it diffracts very well and shows multiple rings. So the software can read each ring and automatically get the center. So the second question is, how do we get STD? All right, look, you cannot answer this one. I need another volunteer. How do we measure STD in this case?
With a ruler.
I like that. It's relatively accurate. It's actually a good way to know what the STD is. Any other answer? How about Michael?
Sample to detector distance?
Yes.
Just wherever the center of the beam hits your sample times the distance, and it's just the distance to your detector, right? So you have settings in the instrument itself where you actually probably have notches as well, right? So you just can like hit certain increments of distance.
Yeah. So we actually do not physically measure it, because then you need a ruler. You have all kind of component in the X-ray beam. You can't just put a ruler there, right? So we do it indirectly. Once we measure STD, we can document it in software. But I always would like to collect something we call the standard sample, just in case the software has some modal error, so position is no longer that accurate. So as a good practice, we always need to measure a standard sample. So how do we know this? It's actually done in a similar fashion based on this method. So how do we do that? What if I tell you I know a polymer, or not a polymer, a crystal that has a well-defined scattering angle? I knew this value. Okay, this is no. Now, the theta we don't need to measure. We know the theta, we know the lambda, so we know exactly Q. However, what we don't know is what this L value is. So as long as we know the D and theta, we can calculate L. It's that simple, right? You only need to know 2 parameters to get the last. So that's how we get the L, is using a standard sample that diffract at the given angle. So we throw the sample in, it's always going to scatter at this angle. We just measure this D value. We, based on this angle, calculate what L. Okay, that specific sample that very popular is called silver bahane. This is basically white powder. We load it into two kapton, and it's always scattered at this Q value for the first ring. Q can be converted by theta angle, so it's always well defined at these angles. Okay, so we see where the first ring is. We can back calculate out, but it's always have a double check. You know roughly STD is, right? If you calculate STD is like 2 centimeters, you physically look at it, you are at about 20 centimeters, you know you're something wrong, right? It always has some values you can get. Okay, so this defines now what the measurement in the Q range. So the scattering angle theta defines how big and how small the Q value is. And we know anything outside means bigger scattering angle, correct? So high Q means larger feature. Anything closer to the center means larger feature. Okay? A little bit tongue twisting, but large at the center, low Q, small at outside. So now comes into when you measure your setup, you need to define what the proper Q value. Ideally, if I have a detector infinitely big, then I only need to measure one setup. I can get smallest scattering angle, which is, you cannot reach as small as where the beam stops by this beam stop. So that defines your low Q. And you cannot measure any data stopped by how big your detector is. That's set at the upper angle. So you can use this very simple relationship. So beam stop size, what's the radius of this? Divide by STD. You can calculate the Q minimum, and Q maximum is what the pixel from your detector. So if you move the beam center to here, you can collect as big as this scattering angle. But commonly, we practice is move the beam stop to the center so we can see any anisotropy scattering in here. So any question for the last quiz regarding how we measure intensity in Q? That's actually very practical, and you probably will use a lot of time in your experiment, okay? So now let's go back to today's lecture. We talked about short range order. We talked about how to measure scattering in liquids or argon gases or amorphous polymer. Those are examples where you don't have any defined order. So, and we know the highly ordered structure is what? A perfect crystal, which every single atom and place are well defined. So we're going to continue to talk about a little bit about crystal, but we will spend some time to talk about somewhere in between. There is some material order specially. This is what we're going to discuss first 10-15 minutes, liquid crystalline polymer. And then we're going to talk about introduction about scattering from crystal, okay? We're going to talk about how you can interpret the different peaks, HLK value, Miller indices, etc. So liquid crystal is an interesting class of material. It's widely used nowadays in your cell phone displays, etc., because it can bend the light and can selectively transform a certain light through it. So it has some terms we need to learn about pneumatic, semantic phases and isotropic phases, etc. But more interestingly, they are a very nice system to study short range order. Or sometimes it's just intermediate order. They're somehow ordered, but they're not that perfect. That's the point. So those molecules are unique. They're typically made of aromatic rings, so they are kind of rigid in the backbone to some degree. And they have some alky chain tails to them. But they have to be rigid to form this long aspect ratio. This is one of the unique characteristics of them. And you can imagine they form this rod or ellipsoidal shape. So what's unique about them is they would go through all kind of different phases, depending on the temperature and processing conditions. So here, let's take a look. On the far right, we have isotropic phase. Isotropic means there's no orientation. If you count where these rods are pointing, it's basically an average of in all directions. If you run a scattering pattern, it basically looks like this. You have a very diffuse halo. You have two kind of degree of order. So one represents what's the average distance between the one of the your rods to another. The other one represents pi stacking. Typically, you have a large aromatic ring, so you have kind of factors comes into play. So if you change concentration on temperature, you can go through the alignment of these materials to call it pneumatic phase. Pneumatic phase is interesting. It has a order in one direction. We know where mostly everybody is pointing. That's an orientation factor, okay? But they don't have long-range order. Means I cannot say I need to go a certain direction at a certain angle. I can reproduce my lattice, right? If I say I go this way, I cannot perfectly predict where the next one is. And the order is mostly one directional. So we can see the directionality, but the packing in this direction is more or less very good. Almost everything at a given distance, we can have a repeating unit in this direction, but not that direction. So now, if we consider the pair correlation function or scattering signal, so scattering in this case is again dominated by structure factor. The individual shape, it will not matter that much because they're in very concentrated system. So in the structure factor, what we are looking for is pair correlation. In a short sense, what we are looking at is repeating patterns in a certain direction. As long as we see a repeating pattern, we are likely to see enough. If they have enough scattering contrast or SLD, we will see a scattering peak from the structure factor. So in this case, the repeating is in all directions, but very weak. So if I repeat a certain distance, I can find another rod, right? So this way, there's another rod. But it's really randomly ordered. Sonia, question?
Yes, I'm so sorry. Could you please explain that part one more time about the short range for repeating?
Yeah. So short range for repeating, it only means at very short range, probably within just molecular range, I have a good chance to find another molecular. Very much like in the case of the liquid water we're talking about. You have a pair correlation with another molecular, so this will give you a large amorphous halo because they're polydispersed in average distance from one molecular to other. So in this case, let's take a look in this direction. It's very hard to define how much distance I need to move to find next molecular in outer plane, in the vertical direction, in our projector screen. But in this direction, we can almost say these will packed very regular. So almost every width of our rods we go, we can find another rod. So you can have a very strong scattering correlation peak in this way, but not necessarily in this direction, okay? Nathan, you had a question?
I was going to ask about that pi-pi stacking pattern that you had mentioned with this isotropic phase.
Yeah.
Where is that exactly in this? I mean, I see that.
No, this is not show up here.
Okay.
If you consider 3D, then you would potentially get it.
Okay, so that's not in that pattern there.
Mm-hmm.
Okay.
So let's talk about two more cases. Semantic phase. Semantic means we have now semi-long-range order. Semi. Maybe we should talk about crystal first. Crystal is something perfect that everybody can understand. I count a distance in vertical and horizontal direction. It's always going to be this distance for me to find the next crystal, right? So you would come into scattering. You would have a pair correlation in this way and this way, which should give you a scattering. Let's say this is beam center, 4 bright spots. Oops, sorry, should not. Let me redraw. It should be this case. Beam center, this order represents the distance of here. And this represents the distance in the vertical direction. If I have to be more accurate, this 2 being going to be closer just because this distance is much bigger than the other one. So it will be inverse. So let me see if I can erase. No? Okay, good. I'll draw it here. All right, so this would be the diffraction you would expect from this particular pattern. You have a Q, let's call it Z. 2 pi divided by QZ will be the distance of this L. As the parent L is bigger than, let's call it LZ, LX. LX is smaller, so if you do inverse of that, that will translate to that. All right? So, now, yeah.
Now, that's just for short-range orders. Is it going to be this similar on the long-range orders too?
No, this is long-range order. This is a perfect long-range order. Yeah, okay. And then another characteristic is we call it high-order peaks. If they're perfect, then you tend to have high-order peaks. So you will not just to show these 2 dots. Instead, you're going to have, we call it 2Q scattering. This is a Q. And at equal distance, we have 2 multiplied by Q to the beam center. And we will have 3Q, 4Q, all the higher order peaks. That's why it looks like a night sky. You get all kind of bright spots. Not a line, not streak, not arcs, but one single spot. Of course, it will change if you have polycrystallinity. So I might just going to spend a little bit of time quickly explain. So if you have crystal, however, in the most beautiful case, you would have one single crystal as big as your beam. Then every single X-ray is hitting at the same lattice spacing. But in many cases, you wouldn't have that crystal. Your crystal may be on the order of microns. And there's hundreds, thousands of these tiny crystals within a sample. And those crystals might be oriented differently. So I'm looking at this way, that way. That's the case what we saw in the example of our silver bahane. It will form a ring. It's called isotropic scattering. So this now, if you think about, there's one ring, then there's another ring, which will be representing for here. Okay, not particularly circular, but you got the point. The distance of Q is still defined by your lattice, but the orientation of the crystal will give rise to an isotropic ring if you have isotropic distribution. And which is likely the case in most of samples. Because it's very hard to grow a crystal on the millimeter size. Some of the inorganics can, but most of the polymer, most of other crystals, are just going to be tiny crystallites embedded in amorphous, and these crystallites are basically randomly oriented. Okay. Okay. So now how about here? Here is the semantic A and C. The difference are they're oriented slightly different. So let's look at semantic A. Why we call it liquid crystalline? So this is isotropic, and this is very commonly called liquid crystalline phase. It has a phase what you typically have. It can you can see ordering in vertical direction and horizontal direction, but they are just not that highly ordered, right? So in terms of when we consider a structure factor for these, you look at them, you see, oh, I see pair correlation function in this direction. So again, you will give out the same scattering peak in here, but we have a few wiggle room in each one. It's not perfect pointing up and down. If I can find two pairs that are oriented slightly differently, we have a pair correlation in this direction. So this will give us a scattering in here, but with a little bit arc. That means you have a certain orientation change. You can find crystals in that directions, but with a slightly angle. If they're perfectly pointed up and down, that will make this transition to a very sharp cut. Okay?
At what point is there a shift between the semantic phase and the pneumatic phase? Because if you look at semantic A and in,
Yeah.
they look fairly similar at first glance.
Yeah. So these two are similar, but the difference in this case is now all the crystal is oriented at the angle. So if we do scattering from this one, you will, instead of see that, you will see one of the rim rotate with respect to the other angle. In this case, the order or pattern, repeating pattern in this, and this is perfect 90 degree. In this, it has about maybe 80 degree. So this will be reflected by, let's assume this will keep the same. So this broader halo is going to be rotating. And broader halo represents the order, the short range order between one rod to the other in this direction, okay? So some of the conjugate polymer diffract similarly, if you remember those kind of phase, just because there's only short range order. Okay, they're not so long range. Any question, Lena, please?
So is the main difference between semantic A and then the pneumatic phase that angle there?
No, not just the angle. In this one, we don't have a well-defined order in the vertical direction. We only have one direction. In the semantic A, we have well-defined order. I should not call it well-defined, or semi-well-defined order in both X and Z. In here, you have X, but not Z. We cannot say, I need to repeat a given rod length to find next stack layer of rods. In this case, I can say a stack layer clearly, another stack layer. Here, I don't have that well-defined. So this means we're going to miss a scattering correlation in this direction, or pair correlation, okay? In a short sense, if you see a repeating pattern, it's going to give you likely a diffraction peak, and this will give you the diffraction peak will be 2 pi divided by distance. Okay, so if you look at this one, look at the wall on that side, it will give you diffraction certainly, because it's very ordered. It's almost like crystal. It has diffraction in horizontal and vertical way, and likely diagonal. We're going to talk about that just in a second. So the point is, you want to know there is existence of not so long range order. But in many cases in the application space, we typically looking at the correlation between the distance of this. For example, if you throw composites, filler in the composite, you're looking at pair correlation between one part of composite filler to another. So you're looking at the spacing, okay? Very much like here, but it's not long range order. Or many cases, I know a lot of you will work on crystal, looking at diffraction. In this case, you're just looking at crystal lattice. In both these two cases, I would call analyze the structure factor is much easier than form factor. Why? You are just looking at a correlation, and you're looking at commonly is a peak from the correlation induced the scattering peak. And all you need to get is 2 pi divided by that Q value to get the real spacing. But scattering from isolated structure to extract form factor is more complex because you don't have peak. Now you need to model the data using the SAS view. So how does this actually impact our results? So this is an example, a pretty good one, to explain how this influence. So let's look at GR. GR is, again, the pair correlation function. It's basically look at probability of finding another material at a given distance. So the top one here basically says it's long range order, means at well-defined distance A, I can find another dots or structure. In the crystal, that means crystal lattice is value A. I move every A, I can find a signal, okay? And we need to talk about convolution. And when we measure scattering data, we will show very sharp, bright spots. If you translate these sharp, bright spots into intensity and Q data, that will define as a very sharp peak. And if you have perfect order, it will be infinitely sharp. However, you can't get infinitely sharp just because your instrument has a certain resolution, right? Your X-ray has a certain distribution in the lambda. Your STD has a certain distribution. So this will always be a finite distance as low as it can go by the instrument. But a lot of time, it's limited by how big your crystal and the quality of crystal. So quasi long range order. The difference is I move a certain distance now, the chances of finding next structure in my pattern, it start to drop. What that means is it means my correlation will lost after a given distance. Okay? So let's go back one more time to here. What I mean by that. If we look at the, let's look at this one. We can find a distance from this one to the next one. It's well defined by the diameter, but there is still some wiggle room, right? So if I move twice the distance, I can find it, but chances is going to drop. I look at 3 times, then there is each one has a certain disorder built into this lattice spacing. So if I say I want to pin down 20 distance, then this might not be sitting at where I'm supposed to be. So it means the longer the distance you move, you lose translational order, a specific term linked to this pattern, okay? So that means you're going to lose all the higher order peaks. That's typical signal of translational order. You would still have this 2 pi divided by A. You would have a very nice correlation peak. But the 2 pi divided by A or 2Q higher order peaks are going to be missed because of you lose translational order, okay? And in the disorder liquids or short range order, where you quickly lost correlation within twice of distance, commonly known as the liquids, you would only have a broader amorphous halo. and the width is defined by the ordering. So one of the way people typically do in crystal analysis is look at where the peaks are, so you know the packing. The second one is to fit how wide your peaks are. This has a defined term called full width at half maximum. So the software would be able to analyze the peak shape and tell you what it is. And if you look at here, the width of the peak is related to the quality of the order. So that's another way people look at the quality of crystal, full width half maximum, okay? So you can use that value to calculate we call it coherent length, which is a parameter you can link to the value of the ordering. Yeah, please.
So like polymer crystals would probably fall into the realm of quasi long-range order.
Yeah,
in this case.
certainly, certainly. So, and for the long-range order in the top one, this only happens in a rare case like single crystal metal. You think about single crystal golds. One crystal, not polycrystal, and within that crystal, it's annealed such that all the disorder, all the dislocation are gone, etc. In the polymers, because of polymer nature and the ULR, it's very hard to form large crystallines with defect-free. So we're always going to have a certain spreading of the width. And the worse the order, the worse the scattering, spreading of your scattering peak. And I'll chat a little bit about probably shear equation in the next lecture to show you what that is. Shear equation is a parameter basically inverse of 2 pi divided by half width used to understand how big your crystalline is roughly. It's called coherent length. It's not one-to-one relationship with crystalline size, but it's fairly close if it's not limited by instrument resolution, etc. So we're now going to move on from this quasi long-range order to really long-range order and talk a little bit about, other than looking at lattice spacing, which is defined by Bragga's law, and very easy to use, right? We know Bragga's law basically says n lambda will be equals to 2d sine theta. Bragg law basically says, as long as you know the distance, you know the X-ray wavelength, based on diffraction angle, we can correlate the wavelengths of construction interference of your lambda versus the d. And combining with scattering vector, if you have Bragg law, scattering vector, you can get the very simple conclusion that d will be equals to 2 pi divided by q, if you know q is, okay? And in this case particularly, n will be equals to 1 if you use the first q, okay? Very easy to understand, diffraction physics. So now, not only it can look at the diffraction from just a distance-wise, based on the pattern of your scattering Q, you can also understand what kind of lattice you have, because different lattice will scatter very differently. You would have a few cases I listed here. Hexagonally is very commonly seen, right? You also have tetragonal, also rhombics, all kind of different crystal is possible. And X-ray could be used to analyze what the crystal lattice is forming in your particular system. Why? We're no longer just looking at in the scattering, we are just looking at the one Q value. In this case, we shoot X-ray to here. Probably easier for everybody to, yeah, let's stay on this page a little bit. If I shoot X-ray to this pattern versus that pattern, I'll ask you what scatter differently. Assuming the distance is the same, okay? This is the same as here. What will be different in this case and this case, which is square and hexagonal case. Isaias, give it a try.
So in the square, if you look at two diagonal points, then the distance between them will be defined by just Pythagorean theorem, where in the hexagonal case, you're going to end up with different scattering peaks at different angles.
Yeah.
Based upon the distance between them.
Perfect, perfect. So in the crystal, we need to know usually 2 parameters to define it. We need to know a vector, assuming it's just a 2D, okay? In 3-dimensional, that's the case. In 2D cases, we need to know the repeating pattern in direction A and direction B, and what's the relationship in the repeating pattern. Then we can replicate this lattice. In this case, if I erase, I probably can't do it. Let's see if this works. Oh no, it doesn't work. I cannot block it. So imagine you only have 3 dots. This should be able to define your lattice, just because you define the direction and you define the angle between these two. Then you just ask it to repeat it again and again in this way, in this way. So you will be able to reproduce the lattice. In this case, although the A and B in terms of length is the same, one goes this way, one goes that way, but the angle between A and B are different, right? So in this, we define as 90 degrees. In this, we define as either 60 or 120, depends on what you look at. So if we shoot an X-ray, we can find repeating pattern in this direction. So direct beam going to be always in the center. We're going to find repeating pattern in the up and down direction. High order peaks are likely, so we're going to add a few data points. Then you would find certainly repeating in the same direction at the same distance. Okay, so you're going to have high order peaks. But you would also have refraction peak coming from this direction. And we're going to explain why just in a second. That's relevant to Miller indices. So not only X-ray diffraction tell you the packing distance, you know where the Q value is? Qx, Qz. You can calculate, hey, my lattice A and B can be simply calculated by looking at 1Q, the first peak, right? That everybody should get it, because we're looking at structure factor in that direction, and we can easily get it. And the second usefulness is you can analyze relative spots between those dots to understand how they sit in a lattice parameter. So in this way, so what the diffraction spots would look like if I shoot X-ray to this particular lattice.
Your vertical direction would be much closer, because now your nearest neighbors are actually diagonal.
Yeah. Yeah. Yeah, assuming this is a perfect hexagonal, okay? So we first need to find where the repeating pattern is. So repeating pattern is going up and down and rotate. Your unit lattice goes this way and that way. Okay? So you would certainly find, don't move, direct beam, a pattern represents basically exactly almost in this shape, because this D and this is the same as the value here. From if we have a squeeze pattern, then that's going to be a little bit more interesting, right? If you have lattice is going the other way, then you have higher scattering peak going from all kind of direction, high order peak. I'm not going to draw it. I'd rather show you a real sample in the later time, okay? So by analyze the scattering peak direction with respect to each other, you can invert back to different lattice parameter, not just the value of A and B, but also how they relatively order with each other. Does this make sense, everybody? Any question for this?
So because your nearest neighbor interactions are at an angle in the hexagonal lattice, would you actually have like a higher intensity diagonal to the beam stop as opposed to vertical?
Yes, you will. You will. We're gonna actually talk about that just in a second. So all kind of different lattice. I want to go into detail, but depending on what ABC value is, basically lattice unit. If we have three-dimensional space, you have x, y, z, x direction repeating unit y and z, and this is just the angle between three different areas between x and y axis, x z axis, y and z axis. As long as you define these 6 values, your lattice is fixed. And there's all kind of lattices being found in inorganic crystal. It's a beautiful area in crystallography research. This is an example. We're not going to go into too much detail, but a lot of time we dealing with those cubic structure. This is a commonly see. In center of the cubic, face center of the cubic, all kind of different orthorhombic structures. But in terms of polymer crystal, we would never form such a perfect crystal. It always has a lot of disorder. So high order peaks are rarely being seen, other than maybe second order, third order can be seen. But we never see, like say, 10 times 10Q or 10th order, etc. So let's look at 3D space. And this is actually called Miller indices. It defines which plane you're looking at. So this is one single lattice unit cell, like Michael suggests. We can easily see the primary ordering in a plane. In the 3D, then you become plane, not just a dot or line. 001, these are just a reference to repeating pattern in the x, y, and z direction. So 0 means there's no, this particular scattering peak is not relevant to any repeating pattern in the x direction. It's only repeating pattern in the z direction. So if you look at that, we highlight in blue, that means the scattering coming from any structure located in the bottom of the plane and top of the plane. Then you could also have 100 peak, 001 peak. That's basically defined in other direction, right? So this means we're looking at the repeatability in the x direction. That means we give it a certain value. We look at x direction repeating pattern, okay, and y. So you can also have more funky ones if you have any order in other direction. 110 peak. 1 means x, so we're going to assign a value at x. Y equals to 1, so we're going to assign to 1. Then we connect all these patterns. But we didn't assign any value in these. So this looks at repeating patterns out in this way. 45-degree angle to where the origin, if we have to draw a diagonal from here, okay? Then you would also have 011 peak, 101 peak. And more challenging one will be 111 peak that everybody can understand, right? If you have repeating structure in this direction. So how about these prime 1 and 1 peak? So any guess? So there's, please,
I
Sonia.
was thinking it's between the angle that would be, or gamma, like half.
Yeah, you can think of this as a complex number or -1. So if you imagine there's any structure, a minus x at equal distance, this is a plane looking at connecting one in z, 1 in y, and the value there, okay? So all kind of different orientation. So if you have very nice crystals in 3D, you're not only going to have the 010, 010, those three are very easy to understand, right? You have simple relationship. But those order will also show up at 101, 110, or 10, or even more complex. And you could also have 2 002 peak. What 2 means is instead of scattering from top, we would have a plane that sits right half of it, because it's a complex number. 2 means half of the length. So that's the plane that's shown here. And we will talk a little bit more in detail, given the time. We're running out for today's lecture. But next lecture, we're going to talk a little bit more about ordering in crystals and show a few science examples how you can index your peaks in your crystal and use that to help you understanding the packing lattice in your crystal. Okay? Any question for today's lecture so far? If not, then let's finish up. Okay?